Cranky Geek Fall 2022 is brought to you by Google, Spearline, Crisp, and Daily. For more information, see the links in the description.
All right, we're back. As I mentioned earlier, AI and using machine learning to improve the WebRTC, the RTC kind of experience is has been ongoing for a while now. Well-known pioneer in AI is Google. That's why I'm extra excited here to have Dan Gunnarsson of Google Meet talk about how they use AI in that application. Dan, I'll let you take it away.
Thanks, Chad. Hi, everyone. I'm Dan. I'm an Eng manager on the Google Meet team in Stockholm. I am really happy to be here talking about some of the challenges and the features that we are offering on the web platform running machine learning. Today, I have two colleagues with me. Matthias Grundman, who is leading our on-device and solutions ML team. That team is also owning the quite well-known ML processing framework MediaPipe. And I have Stefan Ulad also here, who is a program manager on the Meet team, and he is responsible for video processing and also for video quality features.
Yeah, so I'll put them on during the Q&A at the end, unless you need them sooner.
Amazing, thanks. So let's see. There we go. All right. So my talk today will cover a little bit the challenges and the design choices we made when introducing ML-powered background blur and light adjustment running inside of Meet Web using Google Chrome or also other browsers. As a background to all of this, we started running video-based features like face puppets and similar features already in Google Duo on mobile. We also had low light mode, for instance, on mobile for Duo. And when the pandemic hit beginning of 2020, we really saw a surge in usage. And competitors of ours like Zoom were offering a lot of new rich features. One of the big asks we had was to enable users to blur their background or to remove their background to not show everyone in the video calls what was kind of happening behind them. And as everyone was then working from home, this was really something top of mind. So we invested heavily in getting all of that implemented. And as users were doing most of their video meetings on desktops or laptops, the top of mind here was really to get things going in the web browser for us, as Google Meet is purely web browser based on desktop. We don't use a native client right now. Another thing that we saw is that many users don't have ideal lighting conditions when they are doing meetings, and that introduces a lot of difficulties when it comes to equity and representation, and being able to see someone clearly on the video, seeing the face. Different skin tones also impose like an additional challenge. So that was something that we worked on, and I'll cover a little bit later in the speech. So let's jump in. Some of the challenges that we saw when starting to run machine learning-based features on the web is that running inside a web browser is challenging when it comes to performance, because we can't use all the capabilities that a native application can do. In addition, we have to be able to run in real time, and we have to be able to run in real time on a wide variety of different devices. Typically, we are running 30 FPS or 24 FPS, which gives us a budget of roughly 33 milliseconds per frame when processing. When we started building and prototyping around this, we went from something around 60 milliseconds per frame on a MacBook Pro and started optimizing. One of the big things that helped us was using SIMD instructions in Chrome, and that was more or less a 2x speed up. Further improvements that we did was reducing model sizes and optimizing so that we could actually achieve high quality in a high resolution video feed with a fairly low resolution ML model. The choice we made on which pipeline to use for the actual processing was MediaPipe, which is developed by Google and Matthias's team. The main reason for it is that it is widely used within Google, and it also offers a lot of capabilities to the open source community. It's modular. It's designed for media streams. It offers various acceleration on common hardware, and it is possible to use it cross-platform, which is really important for us since we are running on the web. We're also running on mobile devices. We are running on meeting room hardware and other various devices as well. What is great about MediaPipe, and that's also something that I want to highlight here as something that is interesting to the developer community, is that it offers a lot of different models and capabilities as open source. And you can go to the URL that is on this slide. There you can see all these different models, how they are being used or how you can use them, and also what capabilities and what model features they have. Looking a little bit more on our pipeline and how it integrates in Meet. So we are doing our processing sender side. So we are capturing camera. We are inputting that into a media processor or a processing pipeline. And there we do processing. We return the self view to the user, which is an important step because it's important to give users what you see is what you get experience. So you know what is being sent out to the other participants of the meeting. We then encode, we send it through the normal routing using WebRTC and our full stack, and then it's decoded and it's showed at the receiver. Our ML models and specifically our assets when doing AR effects and face puppets and so on are stored centrally in the cloud. So those are downloaded on demand when needed to be used by users. Looking a little bit closer at the actual pipeline, we are using MediaPipe as our processing pipeline for all features. We have a solution, it's cross-compiled into WASM, and in order to run inference, we are using XNNPack, which is highly optimized for running inference, using a library of floating point to enable neural networks. For background blur specifically, then we have a segmentation model that is computing a foreground background segmentation mask. And we have then a rendering step where we are refining and rendering the image together. That looks something like this. And some details around this is that we are using joint bilateral filters to upsample the segmentation mask to have it more smooth. We are using uniform blur with varying kernels to make it look natural and even. And we're using fast 1D separable filters to make that happen. One important part that has been something that we've gotten feedback about, and it's been a bit of a tuning to get it right, is using light wrapping when doing background replacement to prevent bleeding happening around the head, which can be seen in this example. When it comes to accelerating and improving, one major optimization that we landed sometime after launching background blur and background replace as a feature is sparsity. Pretty much the idea there is to set a lot of weights to 0 and make the model smaller. Doing this, you can see the curves here on the right. We end up in a situation where we can go up to something like 70% sparsity and still get a similar level of quality. And this means that we can pretty much get the performance down by 25%, or the computation time down by 25%, and the performance increase, which you can see the red line here. A next step of acceleration that enables us to run significantly larger models is GPU accelerated segmentation. And here we are offloading the inference work to the GPU, and that is really beneficial, but it's also quite difficult. There is a quite large penalty of running things on GPU inside the web browser compared to running it natively on OpenGL due to the nature of WebGL. And at the end of the day, we ended up using fragment shaders to enable the general purpose ML work that is needed for this. And kind of bypassing the WebGL is highly optimized for graphics work. And as you can see here, the result is really remarkable. We are able to run a model that is 4 times as large as on CPU. It increases quality quite significantly, and the latency while doing so is actually smaller than on CPU. The next feature that I want to mention, and it uses some of the same building blocks, is light adjustment. And as I mentioned at the beginning, one of the biggest pain points and the feedback that we got from users was that it's difficult to find a perfect meeting setup in terms of lighting in all conditions. And in this example, it can really be seen well that it's very difficult to see a person's face in backlight conditions. We did different studies on this, and we analyzed different images taken from our meeting rooms. And we saw that depending on the background of the video, like what you have behind you, pretty much a glass wall, a window, makes a huge difference. And something that we call a light reflectiveness value is also very different depending on, for instance, your skin tone, and it ranges from something like 5% up to 40%, and that together makes it hard to make this work right in all conditions. So what we did is we created a feature that is able to improve backlight situations by detecting low light of a person's face, and improving the lighting of the face by using segmentation. This is an overview of the stack, and pretty much what we're doing is that we're inputting a frame, we're getting the segmentation mask, we are using the segmentation mask to do an exposure calculation of the face or the foreground, and we are using that to do an exposure adjustment if we detect low light conditions, and then we brighten only the foreground via WebGL. A few numbers around performance here. This is a mid-range machine that we have in our lab where we're running test scenarios using a real meeting. You can see here that when we have no processing going on, we're around 22-23% CPU load, about 10 watts. And by only running the low light detector, we are just adding a few fractions of percentages. But running background blur on these machines adds roughly 10% of CPU load, or 5 watts of load. The nice thing by using media pipe and being able to chain these different steps or these calculators into a graph is that we can reuse the segmentation mask. So if we are combining background blur with light adjustment, for instance, we only get a slight increase in power, and the CPU here looks similar. So that is really a great feature of using MediaPipe for us. Another aspect of building these kind of ML-based video processing features is that it's quite hard to get them right, and specifically like when having different lighting conditions and having some kind of condition where we are switching things on and off. We have been doing a lot of manual testing in order to get these thresholds right. And this was a screenshot that I thought was fun to share. It's from a test that an engineer was doing on the team, and he was more or less standing before a window reading a book and waiting for the feature to run over a longer period of time and to see if there were any stabilities going on. And it's also running as an automated test now with the test video, which is running the full meat stack and can test for regressions and so on. So that's really helpful. But it's been a lot of work getting there. We did also run into a few interesting issues when running brightening, and this is an actual report from one of our colleagues where we noticed that when we are running brightening, some webcams actually have some color skewing going on, and in this case you see that red is being amplified when we are brightening. So we got some quite funny feedbacks around people saying this looks strange, like I'm getting some kind of color tinting here. So that was something that we also worked on a lot, and were like adding some adjustments around these things to get colors to look natural for all skin tones in all cases. And this feature actually also enabled us to build a lot of process and gain a lot of experience around fairness testing and how to get this right for everyone. And the end result looks something like this. I'm super happy to say that this is really one of our most appreciated features, where we get a lot of positive feedback, and users have been saying, this really enables me to replace or to remove my desk lamp again, because I just don't need it anymore.
This is super interesting. Thanks so much.
Thank you to our sponsors, Google and WebRC.org, supporting web real-time communications. Spearline, guarantee a better customer experience by testing, monitoring, and benchmarking your voice and video communications. Crisp, Crisp's AI solution removes background noise and echo from meetings. Daily, build communications into any application.